So this is a new topic, and this topic, like I said, we kind of struggled with the skills at the end of the first semester. A lot of the, hey, Tate, put it away, right? A lot of the things like solving for y, graphing straight lines, working with standard form, all those things we're going to have to do again now. So maybe we'll get more practice with it. But this is a subject that we do, the main coverage of this is in this class right now. We do a very little bit in Algebra 2, but you're kind of expected to know what the system of equation is from now on in your math curriculum. So a lot of this, as you look at it right now, won't make any sense. By the time we get to the end of it, these objectives will make perfect sense. Okay. Systems of equations. So a system of equations means more than one equation. Okay, one equation is not a system. Two equations, that's a system. So if it's more than one equation, there's going to be more than one variable. And usually, I mean, for us to solve, usually you would expect the same number of equations as the variables you're trying to solve for. So you could have two equations and two variables, three equations and three variables. In meteorology, the equations that we use were 7 equations in 7 variables. Like the wind had 3 variables: east-west component, north-south component, vertical component, like up and down, temperature, pressure, humidity, and condensation. The equations weren't linear equations like we're going to use. They're partial differential equations, but that was the idea. You know, for this class, we're only using linear equations. We're only doing 2 by 2 equations and 2 unknowns. And this is ultimately the kind of problem that we have to be able to solve. And we're not going to solve this one just as an example of something that is solved with system of equations. 15 adults and children attend a magic show that costs $7 per adult and $5 per child. They spent $105. How many adults and how many children attended the magic show? So when you get a problem like that, you have to say to yourself, how many things am I trying to figure out? How many unknowns have I just been asked for? 2. So then in your mind you say, okay, well that means I need 2 equations. If there's 2 unknowns, I need 2 equations. Therefore, you got to be thinking systems. And a lot of times in the math, as you go higher up, you're not really solving, it's not about systems anymore. You're actually doing something else. But in the course of asking the problem, they kind of said there's 2 things you need to know. And so you always have to think, okay, well then that means I'm supposed to be coming up with 2 equations out of this, right? In this particular problem, you know, if I let A be the number of adults and C is the number of children, well, I just said that there's a total of 15. So that would be one equation. A plus C is 15. And since they spent a total of $105, $7 times the number of adults plus $5 times the number of children, that's 105. Okay, those are 2 different equations with those 2 variables. What we're trying to do now in this 3 or 4 lessons that we spend on this is, how do you solve something like that? And what does it mean to solve it? Okay, that's a system of equations, more than one equation. And like I said, when I was doing meteorology, we were doing very complex partial differential equations. You could definitely have nonlinear, you know, curved shapes in there, but everything we're doing is straight lines because that's all we've done so far, right? Linear. We're supposed to be experts in linear by now. We get our master's degree in linear equations, right? So again, this is why we're supposed to have learned how to graph linear equations, so that you can kind of see, you know, what does it look like when I put 2 on the same background. So how do I graph this first one? Y equals 2x minus 3. They're in slope-intercept form. So first you plot the y-intercept, and then what? Right, and then you use the slope, right, to find another point on the line. Okay, how am I going to use the number 2? Okay, you got to think of it like 2 over 1, right? It's got to tell us how much to go up and down and how much to go left and right. Again, if you didn't figure this out in the last semester, you got to keep learning it, right? Because it's not going to go away, right? For this one here, m equals 2 over 1, so that means you go up 2 and right 1. That is not a very good R, but so, and from where do I do that? From the y-intercept, right? From the y-intercept, go up 2 and right 1, like that. Now, that's my line, so let me draw the line. I'm going to hand draw it, even though I could make it a computer line, really to make a point. Okay, then let's use a different color for this next one. How about negative 3x plus 2? The plus 2 is the y-intercept, so I come over here, right under plus 2. And then negative 3 as a slope means down 3, right 1. Okay, down 3, right 1, and something like that. Okay. So the solution to a system, right? We know that this line is made up of all the points that are on that. And you know what? I'm actually using 2 different colors, but they look almost the same. That line is made up of all of these points. How many points are on each of those lines? Infinitely many. Remember, you use 2 points to determine where it is, but there's infinitely many points on that line, right? But there's only 1 point that's on both lines. That's the solution to the system. So when you solve a system, you're trying to find the points that satisfy all the equations that you've been given. Okay. In this case, what does it look like? Is the solution. Remember, first x coordinate, 1, negative 1. Right? It looks like it's 1, negative 1. So solution, 1, negative 1. Now, sometimes I think this one's going to work out okay, but a lot of times if you're trying to solve by graphing, you got to draw a good graph. If you don't draw a good graph, you could be way off. But how could you be sure if that's the solution? If what you see visually is actually the right solution? You could substitute it in the 2 equations and see if it works, right? If it does, it should be that the right-hand side equals the left-hand side. So let's see, if I plug in 1 here for x, 2 times 1 is 2, minus 3 is negative 1. Good. Negative 3 times 1 is negative 3, plus 2 is negative 1. So in both cases, it solves it. So the answer is 1, negative 1. Both. So the solution to a system is the set of points that satisfy all the equations. For us, it's just going to be 2. And for 2 equations and 2 variables, it is the intersection point on the graph. What if it was 3 equations and 3 variables? On a flat surface, you've only got 2 dimensions. So, you couldn't show that on a flat surface. But again, you could have 3 dimensions, just you'd have to have a vertical dimension, where you're not talking about what you would call the plane, you're talking about 3-dimensional space. And yeah, then it could be, 1 point could be the intersection of 3 different lines. What if you go to 4 dimensions? What does it mean to find the solution to a 4x4 system? Is it something you can visualize? Probably not. There's a limit to how much you can see, but in the end, it's all the points that satisfy all the equations that you were given. So we're on 5 out of 20. Oh, sooner or later. What's that? So systems of equations can be more than two equations with more than two variables, and they don't have to be linear, but what we're going to do in this class is going to be two equations, two variables, and they are linear. They are straight lines. You don't have to write that down, just to let you know. So here's the possibility. If you only have straight lines on a flat surface in the plane, there's three possibilities, right? One of them is, and I should change my colors here. In fact, I'm going to do this and use the straight line tool. One of them is, I could do this. That the two lines, like the one we just did, they intersect at a point. Right? There's my two lines. They intersect at a point. That's the solution. If you just have one solution, then it's a unique solution. You know the word unique means? Unique means one of a kind, right? There's only one. Okay. What if the lines are parallel? Do parallel lines ever intersect? No, they don't. So there is going to be no solution because they never intersect. And then what do you think would be the last? There's one more possibility. If you're given two equations, if they don't intersect and they're not parallel, they could be the same line. They could be giving you two equations for the same line. Let's try to draw this so it looks like that. So those are intended to be one right on top of each other. That means every point of the infinite points on one line is also on the other line. It means there's a solution. There's infinitely many solutions. So the way you would say that is it's not unique. There's no unique solution. Most of what we do in this class is finding the one unique solution. Now, the one thing that we're supposed to understand, which honestly, we can say this now. We don't have to really wait till the end of the lesson. What do we know about parallel lines from what we did before? From the lessons we did before, what did we say about parallel lines? They have the same slope, right? So when two lines have the same slope, they can be parallel. But don't these two lines have the same slope? If it's the same line, okay? So what's the difference between this situation and this situation? If the slopes are the same, what's different? The y-intercept is different. So for parallel lines, the slope is the same, but the y-intercept is different. For the same line, they're both the same, right? So we can say that now. Boom. Boom. All right, so this one we say, I'm just going to say M1 equals M2. B1 does not equal B2. For the same line, we know that M1 equals M2, B1 equals B2. So what does that mean about the first one? When is it going to fall under this category? It's not going to be when they have the same slope, because these two represent all the possibilities for the same slope. So these two have to have different slope. Could they have the same y-intercept? Sure, they could intersect at the y-intercept, but they have to have different slopes. If you have two lines and they have different slopes, you know you're going to get one solution. So the only thing we have to say here is that M1 does not equal M2. Good with that? Okay, let's jump. So here's the three ways that we're going to learn to solve. we actually kind of already went over one of them, which is we're going to solve by graphing. You could always just graph the lines using what we did in the past, and then estimate where does it look like they intersect. And then to be sure, plug them in and check. Right. The next two are algebraic methods. They're ways that we can actually calculate that point, not have to graph it. And most of what we do is really related to that. Well, I shouldn't quite say that. Right, these are algebraic. Algebraic. I would say on SOL test, there's a fair number of questions about systems. About half of them, you're really just looking at a graph, and you're having to say from the graph, what are the solutions? So if you know these concepts here, you're going to get a few of those questions right. Just for that, you may not know how to actually solve, but you don't have to because you're just looking at a graph. The rest of them, there's probably some amount of solving here. Okay. So let's solve by graphing. Now, how are you going to graph those two lines? Okay, you could solve for y first and then graph them like slope-intercept. What else? What form of lines are these? It's standard form, right? Remember, what was standard form good for? Finding the intercepts by solving first for x and then for y, right? So you don't really have to go that. If all you're really interested in is finding where they intersect, it'd be much quicker if it's in standard form to graph them by finding the intercepts. Okay. Now, if you choose to solve for y, you better be accurate and you're solving for y, or else you're going to get the wrong line. So let's see. For this first one, right, what is the x-intercept? Cover up the y. If negative x equals negative 2, then x equals 2, positive 2, right? Multiply by negative 1, you're going to get x equals positive 2. So we have the point 2, 0, x-intercept. Okay, what is the y-intercept? Cover up the x, solve for y. 0, negative 2. Okay, how about on the second one? What is the x-intercept? 3, 3, 0. What is the y-intercept? 0, negative 6. Right, so we're just covering up. 2x equals 6, so x equals 3. Negative y equals 6, so y equals negative 6. Okay, let's graph our lines just by plotting the intercepts. And I'm doing this on purpose without a grid in the background, just to show that, there's a lot of chance for inaccuracy when you do this. So, let's see, I'm going to have to go on the x-axis. I need to go all the way up to 3. I'll try and draw it the best I can. On the y-axis, I need to go down to negative 6 and up to negative 2. So it's actually all on the screen right there. So now let me graph my points. 2, 0 would be here. 0, negative 2 is here. So here's my line. There we go. Okay, now for the other one, we're going to graph 3, 0 and 0, negative 6 and draw a line. Okay. So where does it look like the intersection of those two lines is? It's beyond the grid lines that I wrote, but let's say it looks like it's probably about 4, and then it's up as high as about 1 or 2. We're just estimating, right? When you graph, that's kind of what you're left with. You're estimating a little bit. Let's say that that point, I'm thinking it looks like 4, 2, but I can check now. Okay, what if I put in 4, 4, 2? Negative 4 plus 2 equals negative 2. That's correct. And on the second one, 2 times 4 plus 2 equals 6. Oh, what have I got wrong there? Oh, it was a minus. This was a minus. Minus 2 equals 6. So that it checks. It was 4, 2. Right, so you got to do the best graph you can and then estimate and check. So what do you think is coming next? You try. Okay. So try to do the same thing with those. Again, you can solve for y if you want to, right? But you should know how to just do this. I've made these equations so they would actually be pretty easy to do by this method. No.
Exactly.
So look at, this is, again, find the intercepts, right? The x-intercept of this one is, if negative x equals negative 7, then x equals positive 7, right? Cover up that. If y equals negative 7, there you go. So draw those 2 points, connect them with a line. Okay, this one. Cover up the y. X equals negative 8, right? That's that point right there. Cover up the x. If 4y equals negative 8, y equals negative 2, right? Draw your line. Okay, you should see the intersection point. It's down there in the 4th quadrant, and you're going to try to estimate. To me, I definitely thought it looked like it was at 4 for x, but I wasn't sure if it looked like negative 3 or negative 4. But notice that they kind of, in some way or other, are adding up to a 7. So I'm thinking maybe the y is negative 3, because somehow or other they got to get to a 7. And so I said, okay, well, then I'll say 4, negative 3, and if you plug them in, that checks. But again, you got to know how to graph lines. That's why we did that for a month. And if you insist on solving for y, then you got to be able to solve for y correctly. I mean, I'll just say you're not going to be asked to solve by graphing, okay? But you have to understand what it means to be the solution to a system of equations in terms of the graph. It means it's the intersection point, right? Because it is a very inaccurate thing to have to draw and then estimate visually. Now, you could put them in your calculator. There are steps we could do to do this in the calculator, and we'll do this eventually, but not quite yet. You got to understand this concept of what does it mean to solve by graphing? What does it mean to be a solution to a system? All right. Now, substitution is an algebraic method, and there's very finite steps to it, right? These 4 steps are it. So you can break it up sometimes like this. Solve, which is at the end of the line. You know, sometimes that's considered a different step, but that's okay. Or this last one is not actually a step. It's just telling you the answer. It's up to you. I mean, when we start doing them, I'm gonna ask you what was the first step, what was the second step. I mean, these are the things you've got to know when you go into a test on doing this stuff. You got to know what you're doing here. right? So you're going to solve, there's two equations. You're going to solve one of the equations for one of the variables. You choose, okay? You could solve for x, you could solve for y. Usually you look at them and you see which one looks easiest. And then you'll substitute for that variable in the other equation. When you do that, you just reduced it to one equation with one variable. And that's something we can solve with the algebra we already know. I mean, that's the point of solving a system. Somehow you got to reduce this thing from a 2 by 2 to one equation and one variable that you already know how to solve. You good, Ayan? Trinity? Bree, you done? Okay. Yeah, remember these slides are all posted on the website. You don't have to take any notes here, just download them, if you want. Remember I don't check, we don't do notebook checks. I don't check to see what notes you take. Learning how to take notes is something you got to figure out in high school. It doesn't necessarily mean learn how to take every note. This actually means probably learn how to take less notes, but the most important notes. Okay. And I've had this, but it's not a math issue. This is for all classes. I mean, just imagine when you go to college and you're sitting in this big lecture hall with some professor that's down there, and he's just writing away. He's not going to slow down for you, okay? He's moving on to the next thing, and if you didn't keep up with him, too late, right? If you raise your hand and ask, he'll be absolutely rude, saying, "Sorry, figure out a different way." But I'm teaching. I've even heard of a professor once that he was writing on the board like this, and then as he went this way, he had somebody else over here erasing what he had just done. So you had to keep up with him.
No, I mean that we have to do nothing here, that we could just do it online.
Okay, well you can. It's up to you. I mean, this came up with I think I had a parent-teacher meeting recently, where the student said something like, the notes aren't helping me. So then why are you taking them? If you do all this writing and you don't refer to your notes, then why do you take them? Maybe you would have gotten more out of it if you were thinking. Just think about what I'm saying. Yeah. Do you have a question, April?
Do you know what you're supposed to get out of notes? You're supposed to read them, or at least write them, or write them, or at least read them 7 times.
7 times?
That's how it takes to remember the stick in your head.
I never heard it, but I can believe it. But so to me, what I would get from that is not just, okay, then that means I got to go home and read my notes 7 times. What it would tell me is if I'm not willing to do that, then I might want to think about whether it's the whole thing is a useful exercise for me. I mean, there's all kinds of different learners. One of the top lawyers in this country is the guy named David Boies, and he's totally dyslexic. And he is one of the top lawyers in this country, can barely read a book. And he went to Harvard Law School and that. He just sat there and listened the whole time. Obviously, he's really smart to be able to pick it up. But there's all different ways for you to get the most out of it. But it may not include, you actually taking every note. This is what I used to do. I was not a great student all the time, but I would be taking notes, but I would be so tired, that it would just kind of drift off, and now you can't even read what's there, and you really go, this is not helping me at all. But the real thing that wasn't helping me is like being so tired all the time. And you know what? You know why I was tired, which I figured out in the end? It wasn't about sleep. It was all the junk food I was eating during the day. And when I stopped eating the junk food, all the sugar, I used to love Twizzlers. I was really big on Twizzlers. When I stopped doing that, I was able to actually keep awake. That was when I was at Penn State getting a meteorology degree. And at a certain point, I had the first class of the day and then an hour off. And next class, and then an hour off, and then the next class, then 2 hours off, and then a last class of the day. I mean, at the end of the day, you could hardly stay awake. After I changed my diet a little bit, I could sit there and pay attention the whole time. It was just no issue at all. It made a big difference. But again, but I also learned to take less notes because they really weren't helping me. I found it better if I concentrated on what the guy was saying, or girl, or lady. So let's see. Let's solve this one by substitution, right? What did I say was the first step in substitution? Okay, remember, now you choose. So look at these two equations and look at the two variables and tell me which one and which variable was probably going to be the easiest one to solve for. The first one for which variable? Yeah, probably it's going to be for the x because the coefficient is 1. That means at the end I'm not going to have to divide by anything. You don't want to choose, let's say, this one or any of the others because at the last step you're going to divide by something and introduce fractions. I don't want to deal with fractions. So when you have the choice, pick the 1 times a variable. And in this case, there's only one of them. So let's do that first one. So step 1, solve that for, I'll rewrite it. X minus 2y equals negative 6. How do I solve that for x? What's with the x that I've got to get rid of? So I add 2y, right? So I've got plus 2y, x equals 2y minus 6, right? They don't combine. You're just going to write them next to each other. Could you write negative 6 plus 2y? Sure, you could. But I would prefer to write it with the leading term positive. That way I don't have to have a sign, right? So that was the first step. We did it. What was the second step? Okay, so now that means in the other equation, the one you didn't just solve, right? In the place of x, put 2y minus 6, right? Take this here and put it in the place right there. It'll look like this, right? It'll look like 4 times 2y minus 6 plus 6y equals 4. Do you see how I replaced this x with this expression? Now notice, now we've got one equation and it only has one variable, right? This is like going back to the first or second unit that we had of solving equations, right? How am I going to solve that equation for y? Distribute, combine like terms, right? So this is 8y minus 24 plus 6y equals 4. What should I do next? Combine like terms on the same side if you can. So that is 8 plus 6, 14y. It's not minus. It's a plus 6y. The minus is only in front of the 24. Okay, next. Add 24 to both sides. Last step. Divide by 14. So y is 2. Okay, that was the end of the second step. What does the third step say? Okay, substitute this answer into this equation, solve for x, right? So put the 2 in the place of y, and see what you get. It's not an algebra anymore. It's more like evaluating an expression for a given variable. X equals 2 times 2 minus 6. X equals 4 minus 6. X equals negative 2. So again, what was the fourth? It wasn't really a step, but what was number 4 on that side? Right. So the answer is, and you should write it as a point, including parentheses, right? You're going to write the answer is negative 2, 2. So if I would have graphed those two, that's where it would have intersected. Negative 2, 2. What's that? Yeah, if you're taking an SOL test and it says solve the system of equations, I mean, they can't check how you solved it. You could do substitution, do elimination. It's very hard to make, they can't tell you which method to use. Most of what we do in this class, I mean, obviously it depends on what we did before, but also it's important that you see that each step, there's systematic series of steps you've got to take, and be careful about it, Every one of those steps you can do, and you did before. Now you're just putting together to do a bigger thing. Okay, how about this one? If I was going to solve this, this is not a U-try. This is not a U-try. Okay, which one of these equations would I choose to solve for which variable? You're just guessing now. Come on. How many say the first one? How many say the second one? The first one is already solved for a variable. So that step 1 is done. You said both. So if you're lucky enough that they've actually already given you an equation which is solved for a variable, then use it. Then you don't need to do that first step, okay? So this one, you got to why. Some of the homework problems you got to solve. Some of them actually, they gave you one that's already solved. So that first step is done. Okay, so let's say the first step is done. I already have one equation solved for one variable. Go on to the next step. What am I supposed to do with that? Right, I got to take this 3x plus 2, right? And I got to put it in the place of y there. So x plus 2 times 3x plus 2 equals 11. So now we've got one equation and one variable. Solve it using the basic algebra that we already know. First step. Distribute, right? 6x plus 4 equals 11. Next step. Combine like terms. 7x plus 4 equals 11. Subtract 4. 7x equals 7. So x equals 1. Okay, that was the end of the second step. Third step. Plug that answer into that equation, solve for y. Okay. Substitution is a good method because that second variable, you've got a really logical place to go, right? So now we're going to take this 1, and we're going to go up here. We'll say y equals 3 times 1 plus 2. So y equals 5. So what is the point? What is the answer? 1, comma, 5 in parentheses, right? It's not a point. That's terrible. Are you ready for a U-try? Please. So what do you notice about this one first of all? One of them is already solved. So you know that first step is done. I did that. So here's the common mistake that I'm seeing going around. And not many, because most have got this one correct. Right? The answer was 1, 7. 1, 7. But the mistake is, remember, the second step is after you've solved one equation for one variable, then you substitute for that variable in the other equation, right? It goes here, not here, right? If you put it here, then you're going to have an x and a y still in the same equation. And the whole point was not to have two variables anymore, just to have one, right? So, make sure you have to substitute for that variable. And if you do, it looks like this. And you don't even have to do a distributive property this time because there was no coefficient of the y. Now, the truth is that when you have a system and you're going to solve by substitution, you had four options. You could have solved either equation for either variable, and you can do any of that and still be right. Yes. Knock yourself out. Okay, so we could have like four different approaches to this and still get the right answer. Now, usually I'm going to be doing what you should have seen as like the obvious first thing. But if, for example, you chose to solve this one for y first, okay, I mean, you still get the right answer if you do everything correct. But you're probably making it a little harder on yourself, right? Try this one. This one you're going to have to solve one for y. Right, so the obvious first choice should have been you solve this one for y, in which case it should have been negative 3x minus 7. Then you substituted for y here in the other equations. Okay, now, another mistake that we'll make sometimes is, let's say you solve this here, and then you go back into the same equation you just solved and you plug in. And you know what's going to happen? Everything's going to cancel out. You're just going to get 0 equals 0. So make sure you plug in the other equation. And then it's just a little bit of algebra. You end up with x equals negative 2. Then you plug the negative 2 in here, right? Into the result from the first step. And you should have got negative 1. So the answer is negative 2, negative 1, in parentheses, because it's the point. Okay. Are we good? Hey, we got to do word problems, right? Okay, so here we go. Many businesses pay website hosting companies to store and maintain their computer files that make up their websites. Internet service providers also provide website hosting. The cost for website hosting offered by a website hosting company and an internet service provider are shown in the table below. Find the number of months after which the total cost for website hosting will be the same for both companies. Now, because I just copied this out of the book, I'm always thinking to myself, how dated is this in terms of the reality of the numbers or even the process? Do things still work this way? Is this really what it's cost? Because our book is like 10 years old now. And things have changed, especially according to this stuff, it's changed a lot. So let's see. So we're gonna write a system of equations, obviously, because that's what this section is about, right? And we need to come up with two different equations that describe the cost of having your data hosted somewhere, right? So let's say that the x is the number of months, right? And the y is the cost. Now, when you're making a problem like this, you can use m for months and c for cost if it helps you out, Honestly, I prefer to use x and y because I'm just so used to using x and y. And then I know exactly which one I want on the left-hand side and all that kind of stuff. But you can use more meaningful variables if you want. But if these are my two variables, then for this first option right here, it looks like you've got to pay $10 up front, right? That doesn't depend on how many months you're doing this. And then you got to pay $21.95 a month. So what would be the equation that represents that? y equals $21.95 is the cost per month. Made a mistake on that. $21.95 is the cost per month. So I'll multiply times X months, and that'll give me the cost. And then I've got to add 10. Right? What would be the cost equation for the second? Okay, is there a setup fee? Something that takes the place of the 10? No. All right, so it's like in the y-intercept, slope-intercept form, there's no b. The b is 0. And then the cost per month is $22.45 x. So that's a system of equations, right? You got two equations, two variables, solve. Right? What would be the first step to solve a system of equations by substitution? Solve one of the equations for one of the variables. So what do you notice about this one? They're both already solved for y, right? So it doesn't really matter which one you want to deal with. Since this is already solved for y, I will substitute in place of this y, I'm going to put that. I mean, just think of it, it's kind of a transitive property, right? If this equals y and this equals y, they both equal the same thing, right? So they must be equal to each other. So you can just set it equal to each other. 21.95 x plus 10 equals 22.45 x. I hope this works. And it doesn't really, but that's okay. Okay, so now solve. How do I solve this for x? I mean, you have two x terms on either side. So how about if we subtract this term to this side? Minus 21.95x minus 21.95x. What's 22.45 minus 21.95? 0.5. So it's 0.50x equals 10. Divide by 0.5. Okay, so what does x equal? You have a calculator in front of you. What does x equal? 10 divided by 0.5. 20. So what does that tell you? In the context of the problem, it tells you that in 20 months, they have an equal cost, right? This one, you paid more up front, but you paid less per month, right? This one, you paid more per month. At a certain point, the savings that you generate here will pay off the extra that you paid up front. So if you're going to be doing this thing for more than 20 months, then you probably want to do the first method. It's cheaper. If you're going to do it for less than 20 months, use the other method. Then you're saying, yeah, you got to wait 20 months. Okay, I'm just going to show these quickly. I'm not going to solve them all because it's just going too long. But and you don't have to do this, because what I've noticed, even like in my higher classes, when they get systems of equations that involve decimals and fractions, they tend to just deal with the decimals and fractions, which is fine. You have a calculator and you can do that. But you could also like get rid of the decimals and fractions by multiplying. Right? When we solved equations, if we solved and there were decimals or fractions, we learned, you could multiply by something to get rid of those. For example, in these equations here, everything is 0.1 decimal place. What could I multiply by to move the decimal points and not have decimals anymore? 10, right? So multiply each equation by 10 before you start. Now, it could be that one of them you had to multiply by 10 and one of them by 100. In this case, they're both 10. So when I multiply by 10, now I've got 10x minus 90 equals 5y. And 22x minus 31y equals negative 2. So you could take a step and not have to deal with decimals anymore. You don't have to, but there will be a homework problem like that, right? Or You could have fractions. And if you don't want to deal with fractions, then multiply by something to get rid of them. Multiply by the least common denominator for that equation. What's the least common denominator between 2 and 4? 4, right? So multiply the whole equation, both sides, every term by 4. And what about the second equation? What's the least common denominator? There's only one denominator, and it's 2. So multiply like so. 4 times 1/2 x, 2x. 4 times 1/4 y, y. It's 1y. And 5 times 4, 20. Okay, second equation, 2x. Negative 1/2 times 2. Minus y. And 1 times 2 is 2. So you take a step to get rid of the denominators, and now you can solve it like we solved everything else. Right? If you insist on using the fractions all along the way, I mean, if you've got a calculator in hand, you can do it. And like most of the time when I've seen students do that, they actually get it right in the end. So I'm not going to insist that you take that step. But that's what a real mathematician would do. Who's a real mathematician? Okay, Kendall. So that was it. I know it was too long.